Okay, do you see my screen?
Yeah, I can see it. Yeah. Yeah, perfect. Yeah. So you are currently working with Jens, right? I mean, at
yeah.
Okay. So yeah, I think it's my pleasure to invite and have Jonathan Conrad here. So he's I believe a PhD student, kind of toward the senior side, and he has done lots of interesting works on GKP codes and all that many of us have been following, and yeah, he's basically I think in Berlin, basically there's several good people there, and today he's going to talk about lattices, gates, and curves, GKP codes as a Rosetta Stone. So yeah, Jonathan, the stage is yours, and if some, and also regarding the format, normally people prefer questions. It's depending on the people. Some people prefer question towards the end, some along the way. So, what do you prefer?
I'm totally fine with having it more lively. And if you have questions, just shoot at me, and yeah, we'll talk it out.
Okay, so for the audience, you can just unmute yourself and you can ask whenever you have some question or something. So yeah, maybe you could, Jonathan, you could start. I think somehow we see two screens, you see there is slide 1 and slide 2. So
I see. You see the presenter mode. Let me see how this changes it. Wait, let me stop and start sharing it again. Then it's a bit confusing.
Yeah.
So let's see. Oh, wait. Okay, I think I messed up something now. Let's see. Are you still seeing the presenter mode?
Yeah, still it's the presenter mode. So it's we see.
Yes, you see two things.
Yeah, so
and
at the moment
now we see you in the foreground.
Yeah, we see a sticker version of you. Yeah, I think now you're back to the regular. Yeah.
Okay, so I think if I now you should see yourself. Is that right?
Yeah, I see myself. Yeah.
Okay, and if I do this, then oops, wait. Sorry, look a mess. See my YouTube videos. Sorry, I'm really not used to using Microsoft Teams. It's a bit confusing.
So if you press the share button in Teams, usually it will take you to this sub window that lets you choose which window you would like to share from your computer.
Oh yeah, that's exactly what I did. I was asking to share because I have a second monitor. I'm asking to share my second screen. Where you should see my mouse now, right?
Yeah. But it's completely empty, just background. Yeah, and now it's presenter mode.
Okay, wait.
The other thing is that you could download, maybe export it to PDF, and then but maybe you want the presenter mode for your
But I don't care so much. Okay, wait. Try this.
No, it works. It works. This is perfect. Yeah.
Okay.
Yeah, perfect.
That works. Okay, cool, nice. Okay, Cool that we got it figured out. Sorry for the delay. And yeah, all right. Okay, I just start then, I guess. Okay, so this talk today is going to be about the GKP code. And in particular, we're going to focus on a more general perspective on the GKP code. That is, I don't just want to talk about specific ways to build individual codes or the structure of individual codes, but I want to build this conversation towards explaining the general structure of the space of codes. Yeah. So most of you have already thought about quantum error correction before. And if you followed the recent developments in quantum error correction, for instance, Floquet codes, or the general story that goes with it, is that there's more and more often understanding that you want to care about the general space of possible codes and how, as you implement gates or just error correction sequences, how you traverse the space of possible codes. So you go through different codes to end up at the same spot again, or at least you end up at some reference point where you know where you're supposed to be, allowing you a little bit more flexibility and understanding and into the structure of the codes. And what I hope to present to you today is that this perspective in general also helps you to understand the concept of tolerance. So the lens through which we're going to go about this is the GKP codes. So I'm going to start introducing and explaining the GKP codes, what I like about them. And I hope that at the end of the talk, like me, you'll find that the GKP codes provide a very nice formalism to understand fault tolerance in general and to understand how topology really comes into play in quantum error correction. Yeah. So the story is using GKP codes, but I hope that you'll see throughout the talk that it's not limited to GKP codes. It's just like the toolbox that we use. Okay, so that's what we're going to do. I'm going to start talking a bit more generally about quantum error correction and GKP codes and how those come together with lattices. Then I'm going to do something scary. I'm going to talk about elliptic curves and their moduli spaces. This is going to be slightly more mathematical. If you do happen to get lost at some point, if I go too fast, too slow, please stop me at any time, so everybody can keep on track. And then at the end of the day, I package all of this together to talk about what we called fiber bundle for torrents, or what Gottesman and Lucy called fiber bundle for torrents. Okay, so GKP codes. So I assume, since it's quantum error correction typically has a strong background or a strong, like workforce of physicists. So I'm going to talk about physics first. So in physics, for those of you who have studied physics, you know that if you have a system with n degrees of freedom, so those are the n degrees of freedom and labeled Q1 to Qn, you associate momenta to these degrees of freedom. There's a canonical way of doing that. So you have a n degree of freedom system, and you're going to describe it with 2n real numbers. These 2n real numbers form vectors in the so-called phase space that describe your system, and it turns out to be a particularly useful and rich framework to describe physics in. Yeah. So in particular, the dynamics of classical systems is governed by the so-called Hamiltonian function, or the Hamiltonian observable, which is really just a multivariate function of all of these 2n polynomials. You can think of it as some kind of energy function, and the classical equations of motions of such a system is exactly this here. It just tells you that that your coordinates are going to change with the gradient of the Hamiltonian, where the gradient of the Hamiltonian is now flipped by the symplectic matrix down here with a, like it sort of just flips the coordinates, and there's a -1 down here. Yeah, so this is the first bit of where symplectic structure comes into play already in classical mechanics. You don't have to go to quantum mechanics for this. Okay, so why is this useful? Well, we can think about the most simple kind of Hamiltonian evolutions that a system can have. Right? So this here is some generic function of these variables Q1 to Qn, P1 to Pn. So the most simple kind of Hamiltonian that you could think of is one that's simply linear in the Q's or in the P's. that's the most simple kind of Hamiltonian that you could write down. And you could ask, okay, what kind of solutions to these equations of motions do you find for those kinds of like extremely simple Hamiltonians? And it turns out that you can write down, like these are one parameter Lie groups. You can write down generators of solution sets of these kind of equations of motions by what I call the classical displacement operators. Yeah, so these are just operators that take a function of these two n variables, and they're going to shift the function support to somewhere else. Yeah, so these are specifically the displacement operators. In classical land, these displacement operators commute. Yeah, so if you shift along the q-axis first and then shift along the p-axis, or if you shift along the p-axis first and then along the q-axis, there's no difference in the state of the system at the end of the day. So this is the feature of a purely classical system. Okay, so now we go to quantum mechanics. In quantum mechanics, like there's a procedure which you can follow to try to quantize things, to try to go from classical mechanics to quantum mechanics. And within this prescription, what you do is you take the classical Poisson brackets and replace them with commutators. And like you lift all of the operators that act as a Hilbert space. You assume this is a continuous variable system. You assume that you have some infinite dimensional Hilbert space lying behind everything. And on paper, that's what you think. And on paper, what you do is you just replace every operator or every function with the same thing with a hat on top of it. Yeah. So now, if you quantize these displacement operators, something funny happens. That is these. I've taken the displacement operators that we had on the previous slide. I lifted them to quantum operators. So now they take a quantum phase space index X and quantum phase space index P, which are now operators, and shift them to some different value. And it turns out that these quantum versions of the displacement operators now don't commute naturally, but they commute up to a phase that is given by the product of the arguments of these functions. Yeah. So this is exactly the commutation phase that comes into play in quantum mechanics. In fact, this form of the commutation relations, in fact, like this is a different way to write the commutation relations between the Q operator and the P operator that you know from quantum mechanics, called the Weil form of the commutation relations. And there's a theorem, the Stone-von-Neumann theorem, that tells you that that if you have two one-parameter subgroups of operators that commute like this, then this is a form that's unitarily equivalent to like the standard formulation of quantum mechanics. Yeah? In other words, every formulation of quantum mechanics for which you reproduce this kind of commutation relationship is equivalent. Yeah. So this is just to emphasize that displacement operators are relevant for just very basic physics understanding. Okay, so these displacement operators don't commute anymore, but we can still ask what is the part of these, like what subsets of these displacement operators still mimic their classical parts the best. Yeah, and you find very quickly that those are exactly those subset of displacement operators where this product u times b here is an integer multiple of 2 pi. Yeah, because it's in that case that this phase here vanishes, becomes trivial, and the displacement operators effectively become commutative. Yeah, so this is the first pitch that I'm going to make. Yeah, the GKP code, as we develop throughout this talk, is something that you can think about as the structure that stays classical throughout quantization. You start with a quantum mechanical system, you quantize it, and then you simply look at the algebra of quantized operators and you ask, hey, what part of this mimics the classical starting point that we had earlier the best? And it will turn out that the GKP code is exactly this thing. Okay, so that's the first pitch. So now we look at the space of
previous slide.
Yeah. Sorry, previous slide.
Can you show the slide before this?
Oh, this one.
Yeah. Just something I just wanted to check. Okay, so okay, I see. Okay, yeah, thanks.
Okay. So these are the displacement operators, and displacement operators, as you've seen before, they have this very unique feature. These are operators that are labeled by some numbers, and they commute up to a phase, where the phase is exactly the sum product between the labels of the two operators. Yeah. So in the case of displacement operators, the labels of the operators, and therefore all of the phases, are continuous valued, or take continuous support in whatever label set that you're using. But this is often not the kind of operator structures that we care about when we talk about qubit or qdit quantum error correction. Since the quantum error correction seminar, I assume that you all have seen codes before. And most of the time, when people build quantum error correcting codes, you don't start with continuous groups of operators, but you start with something like the Pauli group or the Heisenberg-Weil operator, clock operator groups, which are just the generalizations of the Pauli groups. So these groups of operators share this feature. They share this feature that these are operators that commute only up to a phase, where this phase is given by some product. And in terms of qdit Pauli operators, this phase is always just a dth root of unity. For instance, if you take qubits, qubit Pauli operators always either commute or anti-commute, so they always commute up to a second root of unity. Displacement operators, they take a continuous label set and they simply commute to an arbitrary phase. And it turns out that, in fact, you can, if you start just with like an axiomatic description of Heisenberg-Weil operators, you find you can always embed any kind of Heisenberg-Weil operator into displacement operators. So anything that you can do with Heisenberg-Weil operators and a qdit Pauli operator thing, you can always represent using displacement operators on specific indices that you select to reproduce the correct commutation phases. Yeah. So this is the second aspect of GKP codes that I want you to think about, which is that you can think of GKP codes. I haven't explained yet what they are. This is just a teaser. You can think of GKP codes as a formalism to embed discrete variable quantum mechanics into continuous valued quantum mechanics.
Yeah. So Jonathan,
okay.
Does this always work like kind of a compiler? So let's say I have I have some stabilizer code or some subsystem code or whatever, some code, and then if I go via this, this formalism, can I always get the bosonic version of that discrete variable code?
Yes, you can always think of them as GKP codes simply by, the dumb version of saying is that you can always concatenate.
So you're saying it's kind of straightforward. Yeah? So let's say something that I was thinking didn't get much time to work on is this thing called GKP flocate code, or so basically for flocate codes,
you can do that,
like the bosonic analog of that, one can just do this this continuous thing, and that should give like bosonic flocate code. Huh?
Oh yeah. What I explained to you today, you can straightforward throw it, trying to come up with flocate codes. Yes.
Okay.
For GKP codes, this is particularly nice. For other codes, if you look at cat codes or so, but the structure of the operators is a little bit different, right? For instance, if you have cat codes, right, you don't have a full operator basis, which have the correct commutation relationships anymore, which are also unitary operators. In the cat code, for instance, one of the Pauli operators is like a annihilation operator, which is not unitary, while the other one is a rotation. And so in this case, the formalism breaks down a little bit. So I'm not saying this works for any bosonic codes, but the GKP code is particularly nice and well suited because of the structure of the displacement operators. Okay. So those were the teasers. So now we're going to talk a bit more broadly about GKP codes. Okay. So as I've already teased, GKP codes you want to build out of displacement operators. So now we're back into this 2 n-dimensional phase space. I'm going to write down a generalized displacement operators. So now we have these X operators here, which are the quadrature operators that contain all of the Qs and all of the P operators of a n-mode quantum system. And I define this displacement operator that that essentially just takes one of these quadrature operators, so all the Qs and all the Ps, and shifts them by some 2n-dimensional vector in this phase space, and where the vector is given by this psi operator here. Yeah, so these are the generalized displacement operators that act on n modes of quantum harmonic oscillator systems. So as in the single mode case, these displacement operators again commute only up to a phase. Yeah, and where now this phase is given by the symplectic inner product. So now I have this J in the middle between these two vectors. They commute up to the symplectic inner product of the two indices by which I displace with. And again, you'll see that if this symplectic inner product here is integer, then the displacements will commute. Yeah, that's a core feature. So these displacement operators, they form a group up to phases. But if I multiply them together, I get displacement operators again up to some phases. Yeah, we don't need to care about those too much, for the purpose of this talk at least. And so this is the whole toolbox that we need in order to define the GKP stabilizer group. The GKP stabilizer group is now just a group generated by 2n linearly independent displacement operators, which all commute. Yeah. So the commutation you see you can get from the condition that the symplectic inner product between all of these indices should be integer. And another way to phrase this commutation behavior is to simply look at all of these vectors, and you ask here and you ask about what the dual space relative to the symplectic inner product is spanned by these vectors. And it turns out that if all of these vectors are part of their own symplectic dual, then this is a group that will generally commute. So now the last feature is a tricky one for GKP. And the last feature is that, again, as before, if I have a displacement of some state of a system, I displace it. I can displace it again. I can displace it again. I can displace it again, and I can go on forever. Yeah. So the group of displacement operators that I'm generating here actually is infinite, because I'm just defining this group generation as, take all integer products of all of these displacement operators together. So in fact, this whole stabilizer group that I'm generating here becomes infinite, but because I'm defining it simply by forming all possible products, like the set of all possible products of some set of elements is a discrete set, integer products, right? Like it's a discrete set. So what I end up with is an infinite discrete structure that underlies the stabilizer group here. And it actually turns out that the stabilizer group here is one-to-one with a 2n dimensional lattice spanned by those vectors that we've just thrown out. Yeah. So a lattice, formally is simply whatever is isomorphic to z to the n for some n, or it's the integer span of like n linear independent vectors as we have here. So now the conditions for this stabilizer group to be commutative, to be a genuine stabilizer group, is that the corresponding lattice is a sublattice of its own symplectic dual. Yeah, so this is the basic structure that we.
The similar structure, so let's say in the stabilizer case also, we know, right, that you can take a stabilizer code and you can map to, some code over GF4 by taking 0, 1 omega square. And there the condition is that the classical code should be like a weakly self-dual additive GF4 code.
Yeah, it's exactly analog. Yes.
And this look like weakly self-dual condition, right?
Exactly. This is also in like when I write about this, I also call this the weakly symplectically self-dual lattices. Okay. Yes. Okay. So it's exactly analog to this, right? Like in the classical case or in the CSS construction, right? Like that's where you mostly see this. This exactly comes from the fact that you use symplectic vectors or vectors in a symplectic vector space. You have a similar kind of inner product, but now you define things over F2 or something like this. Right? Or in GF4, right? Like you define a different product, but it's like you can map all of these things to one another. So this is just a basic structure. It's particularly nice because because these lattices give you a relatively nice geometric intuition about how these kind of codes look like. Okay, so now another way to think about this is that this lattice here now represents the set of all stabilizers for a given GKP code, and the symplectic dual lattice corresponds to all the displacement operators that commute with all the displacement operators in the stabilizer group. Yeah. So this is So the symplectic dual lattice precisely corresponds to the so-called centralizer of the stabilizer group. So as if you, like from quantum error correction, you know that this is the place where you want to look for logical operators. And the centralizer, like should contain the stabilizer group, and the complement of the stabilizer in the centralizer is exactly those non-trivial logical Pauli operators, typically, that you care about. Okay, so now we look at a simple example. How do we actually come up with a GKP code?
Hey, sorry, Jonathan,
one,
can I ask something
yeah.
about the previous slide? Just to clarify, so there are this psi1 up until psi2n. So those are just integers in this vector xi, right? Is that what those are?
No, psi1 to psi2n are vectors in R to the 2n. I have 2n independent vectors in R to the 2n.
Okay, I see.
So they form a basis.
Thanks.
Okay. Right. Okay. So now this is the first example. I hope things will be a bit clearer after this. So I'm going to start with the simplest example. We're going to set n equals 1, where at a single mode, our phase space is two-dimensional. It's R to the 2. And we're going to try to construct a GKP code that has a commuting stabilizer group, as I've discussed before. So the simplest way of coming up with the GKP code is to start with a so-called symplectically self-dual lattice. Yeah, that's a lattice where L equals L perp. A way to come up with a symplectically self-dual lattice is to take a symplectic matrix and to simply take its rows and have the rows generate the lattice as its Z span. Yeah. So here what I'm doing is I'm taking a symplectic lattice, which I call M0. In the picture, I've simply picked M0 to be the identity matrix. So it's identity one matrix. I have two vectors, one with components 1, 0, one with components 0, 1. These are the two vectors that span my lattice, my square integer grid. Yeah, and this turns out to be exactly a symplectic lattice. Yeah, well, because if I conjugate J with identity, then it's still going to be J. Yeah. Okay, so this is a symplectic lattice, and we want to build a GKP code that's a little bit that's less trivial out of this. Okay, so first thing to recognize is that for a symplectically self-dual lattice, where L equals L perp, so we go back to the slide, L the stabilizers, L perp the centralizer. If L is equal to L perp, that means the stabilizer group is exactly equal to the centralizer. What that means is that there are no non-trivial logical operators. Therefore, but we still have a full set of commuting operators that stabilize our code space. So what we get in this case is precisely a stabilizer state. Yeah. So we have a bunch of stabilizer operators that fix a one-dimensional Hilbert space, and that's exactly what the structure of stabilizer states look like. So that's when L equals to L perp. So now we want to tweak L and L perp a little bit, so that there's a bit more, so that there are some non-trivial vectors in L perp. So the trick by which we're going to do this is that we're simply going to take the symplectic, take the GKP lattice, which is now just a Z squared grid, and we're going to scale the stabilizers, all of the vectors corresponding to the stabilizer group, by some factor that's a square root of an integer. Yeah. So for instance, here I've taken the Z squared grid as scaled by square root of 2. So now that's what you see on the thick lines. So now the thick vertices, they all indicate the stabilizers of the GKP lattice. So as you've scaled up the integer lattice, right, now you've created space for logical operators. That is, now all my vectors are like square root of 2 multiples on one component and square root of 2 multiples on the other component. So if I want to have a product that's an integer with one of these vectors, you simply have to take other integer vectors and scale them by 1 over square root of 2. So now as you've scaled up the stabilizer vectors of your GKP lattice, the logical vectors will have shrunken, but they now exist. Yeah? So now you have created the situation where the dotted lines correspond exactly to the logical vectors of the corresponding GKP code. And as you see here, if I have a logical vector, right, I apply a logical operator twice, a logical vector twice, I get back to the stabilizer lattice. Yeah. So this is exactly the structure that we want for qubit codes. Yeah. For a qubit code, we want a logical Pauli X or Pauli Z operator, which is such that if we apply it twice, we get back into the stabilizer group. Yeah. And then this, so that we create logical identity. That's the structure of these kind of codes. Yeah. So here in this picture, which is stolen from the original GKP paper, the situation that we created is we've started with a Z² lattice that's symplectically self-dual. We've scaled the stabilizer lattice up, and now we've created a sublattice structure where the symplectically self-dual, where the stabilizer lattice corresponding to 6 lines is a sublattice of its own symplectic dual given by the dotted lines. And there are exactly 4 different code sets in this kind of construction so 4 different lattice code sets of L and L symplectic dual corresponding precisely to the 4 different logical Pauli operators that you can have. Yeah. So if you remind yourself of Pauli-based quantum error correction, you typically look for logical operators in the group quotient of the centralizer of the stabilizer code modulo the stabilizers. Right. So here the centralizer maps to the dual lattice, the stabilizers map to the direct lattice, and so now you look at the lattice quotient. Yeah, and so this is exactly how you build the code. And it turns out that, you know, like in more generality, if you count the structure of these kind of codes, you find that the unit cell volume of the stabilizer lattice corresponds exactly to the encoded logical dimensions of the corresponding code. Yeah. So before we've counted the number of logical Pauli operators, and you know that if I have a d-dimensional quantum system, then I always have d² logical Pauli operators. So you can go backwards and use this trick to count the number of logical dimensions that you've encoded. Okay, so that's the structure of the logic. But what about noise? So we're doing quantum error correction. We want to be able to do something non-trivial about noise. So in this construction, what has happened is we've started out with the Z² lattice. We've created long stabilizers and short logical operators. Yeah? And the short logical operators, the length of the logical operators, now exactly dictates the length of how far noise is allowed to push our system to create a logical error. Yeah. So if I have under some physical assumptions, some displacement noise channel, then the length of the shortest logical operator is exactly the length by which my system, kick my system around, error on the system. So that's exactly going to be our definition of the distance. It's going to be the Euclidean length. Now it's not Hamming norm, but it's Euclidean length of the shortest logical operator, or of the shortest length of a logical displacement that is not a stabilizer displacement itself. Yeah. So this is the norm, and since in this case we've used such a simpler characterization, we've done the scaling construction. It turns out that the distance under this definition of the GKP code is just directly proportional to the length of the shortest lattice vector of the symplectic self-dual lattice that we started out in. Yeah. So this is the most basic construction for GKP codes. I think if you understand this as an example, you understand all other constructions of GKP codes quite straightforwardly.
So basically, you know, I mean, I think in stabilizer codes, right? Like people know that, calculating distance is NP hard, and here you map it to, lattices, like shortest vector problem of lattice. Like, does this imply that for GKP code, the distance is also like NP hard to calculate?
Oh yeah. Yeah. I mean, yes. Yeah. I mean, like that's a generic thing about these lattices. Lattice problems are hard, and you can solve. Also, decoding, for instance, you can solve by approximating the closest vector problem, right? So there's a whole can translate all of the quantum error correction features into lattice problems, and you'll see that they're actually hard things to do. No, which is consistent because actually, if I remember correctly, it's a bit of a chicken and egg problem, but I think the proof of the hardness of the shortest vector problem actually comes from the hardness to find short to find like distance of classical arithmetic codes. Right? These proofs are like always built on top of each other. Right, but yeah, it turns out that people who like combinatorial things have thought about hardness of decoding and so on a bit earlier. Okay. Right. Okay. So this was the construction for the simplest kind of GKP codes in n equals 1 dimension. So now I want to take a big step forward, and we want to look at all the GKP codes. So you imagine we've started out in this previous construction, we've simply started out with a symplectically self-dual lattice, and we've scaled. So now we're just going to restrict to the class of all of those GKP codes, and we're going to look at all of the GKP codes that we can obtain by scaling a symplectically self-dual lattice. Yeah. So as in the previous construction, every symplectically self-dual lattice you can generate using the rows of a symplectic matrix. So now, well, I mean, the association is straightforward, but like every symplectic matrix gives you a symplectically self-dual lattice. So the space of symplectically self-dual lattices you can characterize by understanding the space of symplectic matrices. For lattices, there's a simple but very important nuance that also plays into the hardness of decoding and shortest vector problems, as you just pointed out, which is that for lattices, there are given a single basis is not like fully characterizes the lattice, but there can be many different bases that give rise to the same lattice. Yeah, so for instance, in the previous example here, but I can generate the lattice by two basis vectors, one pointing here and one pointing here, but I can equally just take a sum of those lattice vectors. That's going to be an equally valid basis vector, and taking the diagonal element together with one pointing here is also a sufficient or full like generating set for the lattice. Yeah. So if you start to count how many options there are, you'll quickly find out that there are actually infinitely many lattice basis choices that you can make for any lattice that you want, that you look at. And this like infinitude of possible choices of bases, which can be arbitrarily bad, as in long or short, like this is exactly the source of why lattice problems are hard. Yeah. Okay, so lattices are generally parameterized by some symplectic matrix up to a basis transformation, where now my basis transformation is also in the space of symplectic integer transformations on the basis vectors of the lattice. So now these are the arithmetic structures that we need, and we can actually just write down the space of all possible lattices / GKP codes as the space of all symplectic matrices in 2n dimensions modulo left. Now this is a left modulo. This is not a set minus. A left modulo all of the possible basis transformations that it can apply to the corresponding like matrix, if you interpret it as a lattice basis. So the space is pretty interesting. You can actually prove that it has a finite measure, and there's all kinds of funky stuff that people know about it. And so throughout this talk, the goal is to characterize these kind of spaces a little bit better. Yeah. Okay, so we're going to go back to n equals 1 dimensions, and we're going to try to think about different, like, we're now just going to start to list like different ways to think about the space.
So basically, Jonathan, Jonathan, like basically, so I think basically the crux of this work is kind of this observation that the general GKP codes correspond to this modular space, and then basically using ideas from the modular space, you basically you characterized and studied it in detail and all that.
Right. Yeah, I mean the core of this work was really to understand this moduli space a bit better, right? To understand the different interpretations of the space, and to understand how to map to other objects and how to characterize the topology of the space in particular. Right. That's
very nice. Very nice.
Yeah. So exactly, we're going to look at one way to look at these spaces, and we're going to look at it again in the case of n equals 1. So single mode, we're back into the phase space of dimension 2 and lattices of dimension 2. So in this kind of scenario, we can do a very simple transformation. So any lattice in 2 dimensions, I can rotate so that one of their basis vector points along the x-axis, and that the other vector points along the positive, somewhere positive along the y-axis. Right? Like this is always one one choice of bases that I can make up to a rotation, up to like flipping the lattice along the x-axis in some way. Okay, so I'm going to do this, and I'm going to, instead of thinking of r to the 2, I'm going to simply map all my vectors to complex. Like I'm going to map r to the 2 to c to the complex plane. Yeah. So now my lattice is parameterized by this. I have one vector that's just number 1, and the other lattice basis vector is in the complex upper half plane. Right? This is the vector tau. So this is how you can think about the lattice. The lattice is now generated by the two vectors 1 and tau in their integer span, and this is a complex lattice in the complex plane. So in this representation, when I implement a basis transformation, what I actually do is, I mean, I'm still going to fix the lattice. Well, I'm still going to keep one of the basis vectors on 1, which is something that I can always do up to the rotation. In this parameterization, what happens under a basis transformation is that I'm going to execute a Möbius transformation on this parameter tau. Yeah, so a Möbius transformation is just I have this matrix ABCD, and I'm going to map tau to A tau plus B and C divided by C tau plus D. Like it's just a funky transformation, which I find is useful to develop the pictures that we try to draw. Okay, so what's an example of this? So I'm going to start in this picture. In this picture, I'm drawing the upper half plane. Right? So this is just a complex upper half plane with a real line down here at the bottom. And as you can think, the perfect square lattice is going to be generated exactly by by 1 along the x-axis, or the real axis, and by the component I along the imaginary axis. Yeah, that just gives you a square complex complex square lattice. Yeah, so that's a lattice that in this picture sits exactly just right here on this blue thing down here. So if I took this lattice and I squeezed it a little bit, yeah, what's going to happen is that I'm going to make the real dimension a little bit shorter, and relative to that, I'm going to make the complex one a bit longer. Yeah, so as I squeeze the lattice, what I'm going to do is I'm going to take this point in the upper half plane and I'm going to move it upwards. Yeah, so you can see that this line parameterizes all rectangles, all rectangular lattices with arbitrary squeezing. Yeah, so that's exactly what this line up to infinity does. If you squeeze it infinitely far, right, remember that the squeezing in this picture is always happening by symplectic matrices, which always preserves the volume of the unit cell. So if I squeeze it infinitely far, one of the vectors gets infinitely long and the other one gets infinitely short. So my lattice distance is going to go to 0, and you'll see that the point where this happens is exactly at imaginary infinity, all the way up here. In this picture, I've also drawn a different feature, which is I've drawn in the tiling by basis transformations. Yeah, so it actually turns out that like this sp2z is a lattice under a different definition of lattice in sp2r. Maybe this doesn't matter so much, but effectively what I've drawn in here is this tiling that shows you all of the equivalence classes under basis transformations. Yeah, so a lattice that I represent here on this red point here is going to be exactly the same thing down in this unit, in this fundamental domain back here on the right. And it's also, now this is a bit tricky, but it's also the same as, like the lattice indicated by this point down here, given by the reflection along this arc. Yeah. So this is just a very fancy way of drawing lattices, or the space of lattices. The point is that you can parameterize it by the upper half plane, and for some proofs, understanding this picture, things get easier. Okay, so this was the second picture. And now, okay, we're gonna forget about this upper half plane thing for just a second. I'm going to give you one more picture. Yeah. One more picture is given by the following. Again, I'm going to take this lattice parameterized by the two complex numbers. Since I've complexified my lattice, I'm also thinking of my lattice as sitting in the phase space given by the complex plane. So now what I'm going to do is I'm simply going to represent the lattice by taking the complex plane and modding out by equivalencies up to shifts of the lattice. Yeah. So this modding out has specific feature is that if I take C and I mod out the lattice, right, I get a torus. And the torus is precisely such that its first homology group reproduces the lattice that we started out with. So all the information is still there. This is the full description of what we started out with. So now you can imagine the following picture. I've shown you earlier that in this like scaling construction, like stabilizers and logical operators, they're just like proportional up to some constant. So what we're going to do is we're going to think about my lattice vectors here as the logical operators of a GKP code, the logical displacement amplitudes of a given GKP code. So now you've created a picture that's very close to what you know from the Torah code. Yeah? So you've started out with a lattice where the lattice vectors label Pauli elements. And as you take phase space and you mod out this lattice, you've created a torus where the two homology elements correspond to the two non-contractible loop in the homology group of this torus. And funny enough, the symplectic inner product between the two lattice vectors in the space that you've started out with is exactly a different way to characterize the intersection number for two homology, for elements on the homology groups of these things, right? Like this, like if you read literature about
so this is also like same thing, right? That we see in topological codes, right? They like using first homology group, you get the, I mean the logical operators.
Yeah, it's a bit of a different route that we're taking here, right? Because here we're not we didn't start with we didn't start with the chain complex, right? Like so the way that you build this is a little bit different. But the funny observation and the reason why topology starts to come into play is actually sort of, you can think about it the reverse, right? Like given the homology group of some Riemann surface of some torus or so, you can always, like homology groups over Z, you can always represent using integer vectors, right? Like these are just like some high dimension integer vectors. And there's this thing that if you look into literature about intersection numbers, is that the notion of they call it the algebraic intersection number. It's like you can actually calculate intersection of loops on homology groups in general using a symplectic inner product between the two corresponding elements. But like so it's not so the literature also comes into the structure, like looks into the structure from the other perspective, and the reasons again just the same, right? Like if you have intersection numbers on Riemann surfaces, on tori or whatever, right? You want the loops, you want the crossings to have a different sign if you reverse the direction of how they cross, right? And that's where this -1 in the symplectic form starts to matter. And then the two different dimensions, and then the two different directions just like tell you, okay, hey, is this one thing like locally x-axis or the other, or locally y-axis? Okay, so that's how you go from GKP codes to lattices to tori. So now for the rest of the day, what we want to do is we want to think about tori. Okay, so now I've drawn a point onto the torus. What does this point mean? So in the space above, or at the space at the bottom, if I put a point on this torus, what the information that you have about this point at the end of the day, since we've associated the homology group of this torus with the group of logical operators of the corresponding GKP code, the point of the torus is going to contain information about a displacement up to logical operators. Yeah, because if I have a point on the torus, it doesn't know whether it comes from having wound around the torus once or twice or 5 times or not at all, right? Like so a point on torus doesn't know any information about winding or about homology. Therefore, this is a point that's completely agnostic of logical information on the corresponding, for the corresponding operator. Yeah. So this is precisely why you can understand these like points on these tori as syndromes or labels for error sectors of the corresponding error correcting code or the corresponding GKP code. Yeah. So this is the full characterization that we have of GKP codes. Yeah, we have this tuple E, which is given by a complex torus, which we obtain from taking C and modding out a complex lattice. This characterizes the structure of the code and that of the logical operators. And we can add an extra piece of information to this, which is just a point on this torus. And this point is going to have the interpretation of a syndrome of the corresponding code, or just label for the error sector for the corresponding code. So if you open a book about elliptic curves or about complex, algebraic geometry, you'll find that this kind of structure is exactly what people call an elliptic curve, right? So there are 5 billion different ways of writing down an elliptic curve, and having a pair of a complex torus together with a point on it is exactly one of those ways to write down the structure of an elliptic curve. Okay, so this is how we start, and now I'm going to explain the more complicated way of looking at elliptic curves. So elliptic curve, if you probably have heard, so it's more likely that you have heard of elliptic curves from the perspective of crypto. Yeah, and there's like elliptic curve cryptography and so on, which really just comes from the fact that solving equations of this sort, right? Like these are sort of cubic equations over some finite fields, for instance, or over the integers or over the rationals, is generically a hard problem, right? Like that's where all of this like post-quantum crypto, elliptic curve crypto stuff comes from. In our case, we do something much more simpler. We're going to stay on the complex numbers, and in the complex numbers, polynomials are always super easy to take care of. Okay, so what I'm going to explain now is that this elliptic curve that I've written down up here is equally characterized by polynomial equation. It's down here. Yeah, so here we have a polynomial equation given by y squared equals 4x cubed, some parameter g2 and x, and a different parameter g3. So I'm going to the relationship between the elliptic curve and the lattice that we started out with is given by the so-called Eisenstein series. So if that here appears, this is basically it looks a bit like a Riemann-Zeta function, but in complex numbers. So what I do is I'm going to take the lattice. I'm going to sum over all of the non-zero lattice vectors, and I'm going to take it to some negative power k. Okay. So this defines me two numbers that are functions of the lattice. So I'm going to have the number g2 and the number g3. You don't really have to understand these functions so well here. But what's important is that you can prove that just knowing these two complex numbers uniquely fix the lattice. I mean, that sort of makes sense. The lattice, that we started out with was uniquely fixed by two complex basis vectors. And so now it's not just by counting the dimension of possible parameters. It makes sense that you can also find two other complex parameters that characterize the lattice in a similar manner. So these are the two functions that go into this polynomial equation down here. And it actually turns out that if you try to solve this polynomial equation over complex projective space, I don't want to explain why, but yeah, it doesn't really matter so much, is that you actually find solution sets to these polynomial equations as the so-called Weierstrass P functions and its derivative. Also doesn't matter so much, but what matters is that these are functions that take values on the torus. Yeah, so this is how you go from polynomial equation to a function, to a solution set of the polynomial equation, which is periodic on the torus. And you know that the torus is one-to-one with lattice. Yeah, so I hope that this illustrates the connections. Yeah, so in this kind of picture, the set that we're starting at right now, this is exactly the kind of the syndromes that we look at, and like solution sets of these kind of polynomial equations have a certain kind of group structure, similar as addition has on the torus, and that's like the group structure is where all of this cryptography stuff comes from. Okay, so that's a different way to look at lattices. So since we live in complex space, and so we're looking at polynomials over the complex numbers now, our life in analyzing these polynomials is actually pretty simple. That is, like if you've learned some math, you know that over the complex numbers, I can simply factorize every polynomial into its roots. So that's what we're going to do here. I'm going to take this polynomial, I'm going to factorize it into the three roots, E1, E2, and E3. And you can actually solve, and you'll find that the three roots actually just correspond to this Weierstrass function evaluated at the 3 points in phase space. So one corresponding to half of the first lattice vector, half of the second lattice vector, and their sum. Yeah, so this is a structure of the roots of these polynomials that characterize our lattices. So why is this relevant? Well, okay. So first of all, what you see is that in the earlier case, I made this example of what happens if you squeeze a lattice infinitely far, right? Like if I squeeze a lattice infinitely far, that means one of these vectors is going to get super long, and the other one is going to vanish. So as one of these vectors down here vanishes, so W1 is going to become 0. W1 here is going to become 0. These roots will start to coincide. Yeah. So exactly the point where the distance becomes 0 is the place where these roots start to coincide and start to like become degenerate. So this is something that we can characterize as the singularity of this polynomial equation. And so there's this function called the so-called discriminant function delta, which which is really just like the product of all of the differences between the roots of a polynomial squared, but this doesn't matter so much. And that just like is a function of the lattice that characterizes whether or not roots overlap, or how far or how much they overlap. And it turns out that it's modular discriminant here you can also write in terms of these G2 and G3 functions that we've seen earlier. Yeah, so now this discriminant function is G2 cubed minus 27 G3 squared, and we know that these roots overlap. Therefore, our GKP code and the lattice have distance 0 exactly when this function here is 0. Okay, so this is the example that I've just illustrated, right? Like this picture that we've seen earlier. If we start with the lattice, we squeeze it infinitely far. Two of these roots are going to start overlap, and then this discriminant function is going to vanish at some point at imaginary infinity. Okay, so this is essentially the thing that I've just outlined. We can think of the space of. So now we're like pretty close to characterizing what the space of all possible GKP code lattices is. One secret information that I didn't tell you is that there's some freedom in choosing G2 and G3. In particular, I can always normalize them. Right? I can always normalize G2 absolute value squared plus G3 absolute value squared equals to 1. So this I didn't write onto the slide, but this is an important piece of information, because what is this, right? Like G2 and G3 were two complex numbers that uniquely label the lattice. Two complex numbers live in a 4-dimensional space, but if I now normalize them to absolute value square to 1, then I'm cutting down the dimensions, and I'm actually, rather than living in a space equivalent to C2 or R4, I'm going to break it down onto the 3-sphere, right? S3, right? Like that's exactly the space of two complex numbers that are normalized to sum to 1 on the absolute value squared. So that's a space in which these two complex numbers now live. So now within this space, we've just discovered that there's extra polynomial equation that we don't want to be 0 for the distance to not be 0. Yes, so we have this polynomial equation G2 and G3, G2 cubed minus 27 G3 squared. When this is 0, then we also know we have a distance 0 code. So that's something that we want to exclude. So now this explains this like picture here. It actually turns out that within the 3-sphere, within the like normalized domain, G2 cubed, G2 squared plus G3 squared equals 1. The space of all the solution set of this polynomial to be 0 corresponds exactly to a knot, corresponds exactly to a trefoil knot that I've drawn in gold down here. And this is exactly now the characterization of the space of all GKP codes that we have. Yeah, or the space of GKP codes you can label by the space, by the 3-sphere with this knot here cut out. Yeah? And so this knot here is described by the polynomial equation up here. Is going to describe a topological defect in the space of all possible codes. So there's some funky math that you can do to prove the relationships to distances and so on. But yeah, this is not what. Yeah, but yeah, I want to move on to Clifford gates. Okay, so if we employ gates, what are we doing? So when we apply gates to GKP codes, right? Like you remember, our lattices were such that the X Pauli operators on one axis and the Z Pauli operators is the other basis vector. And if you apply Clifford gates, what you effectively want to do is you want to apply basis transformations on these two axes, right? Like for instance, you interchange X and Z, that corresponds to a logical Hadamard gate, or maybe you do something like you map Z to Z and you map X to X times Z, right? Corresponding to a logical phase gate. For the underlying qubit code. So in the picture on lattices, for the corresponding code. So I go from one fundamental domain into another fundamental domain into an equivalent point, but it will have crossed the boundary in a non-trivial manner. On the space of lattices, right, I take the lattice, I'm going to interchange some of the basis vectors or add them up in a non-trivial manner. My condition now is that as I do this, I don't want the roots of the polynomials that I looked at before to coincide in this process. Yeah, because I don't want to go through a distance zero code as I do this deformation, as I do this implementation of the Clifford gate. So now what do we have? We have these 3 points that label the lattice fully, where two of these points correspond precisely to 2 of the logical Pauli basis vectors or Pauli operators of the code that we look at. And as we implement a logical Clifford gate, we are looking for a deformation or a permutation of these points, which is such that the points never coincide along the path. Yeah. So this is precisely the break group. Yeah, this is precisely the break group on the 3 strands corresponding to the roots of this elliptic curve equation that I've written down here. And this is exactly the explanation why why the homotopy group of this like 3-sphere minus is not corresponding to exactly the space of all possible codes is exactly the break group. So this is some funky correspondences. Okay, so this now puts us into place to think about what fault tolerance meant, right? Like I already sort of like gave a bunch of hints earlier. I said I want to think about a fault tolerant implement, or I did use these words, but I want to think about a fault tolerant implementation of a gate as a as a transformation in the space of codes that always stays at some bounded distance, at some distance bounded away from 0. Yeah. So if my distance throughout this whole trajectory in the space of codes always stays some distance bounded away from 0, then there always exists some noise parameter that's small enough that I don't apply logical operators, that I don't implement logical errors along the path. So another way to make this picture a bit more rigorous is a paper that Daniel Gottesman and Lucy Zhang wrote ages ago that which they called fiber bundle fault tolerance, and their picture is very similar to the kind of pictures that I've just drawn. Right? Like it's a bit more rigorous, and I hope that I can explain this very briefly. So their proposal to classify fault tolerance is to look at the so-called Grassmannian of a physical Hilbert space. Okay, so Grassmannian, it's a big word. All that this means is that you look at a physical Hilbert space and you ask what is the code in the physical Hilbert space. Well, like a code is a choice of subspace, and the set of all possible codes is simply the set of all possible subspaces of a fixed dimension of a physical Hilbert space. So now you can think if I try to unitarily implement some gate that implements a logical gate, right, in this on some code, what I'm going to do is I'm going to start with my code space in this physical Hilbert space, and I'm going to move around in the physical Hilbert space until I end up back at the code that I've started out with. Yeah, so you want to traverse loops on this space of all the possible subspaces in order to implement logical gates. So now the fiber bundle that they're building is exactly this, right? Like they take the Grassmannian, which is a manifold of all possible subspaces of a given physical Hilbert space, and then on top of every point in this Grassmannian, so on top of every subspace, they simply paste the subspace itself, right? That's the code space. So now you have this manifold, or you have this fiber bundle, where you have the space of all possible code spaces, and on top of that, you have the code space sitting in itself. So what you now want to do is, as you implement a logical gate, but what you want is that you want to traverse a loop across a space of different subspaces, but you want to do that such that my logical vector that's up there in this fiber changes in some very concrete way, but you want it to change in a manner that's robust to noise. Okay, so the proposal that they had is essentially this. The proposal to classify fault tolerance is to say that fault tolerance gates are such that I can find this classification in terms of Grassmannians, where the implementation of a logical gate up here necessitates to wind around a topologically non-trivial feature on the Grassmannian, on the space of all possible codes. There's a bit of a lengthy explanation. If you look at our example, this is exactly just what's happening here, right? We look at the space of all possible codes. You can think of associated to the space of all possible codes some logical code space if you want, and we see that as we try to implement logical Clifford gates, we always wind around some topologically. We need to wind around some topologically non-trivial feature of the space of possible lattices. Okay, so this is the final picture that explains this. So here on the bottom right, you again see a picture of the three-sphere with the trefoil not cut out. Right, this is so three-sphere is two spheres with their surfaces identified. I have this trefoil knot defect sitting inside, and to every point in the space, I can associate a torus of which the homology elements correspond exactly to my two logical operators of the GKP code. So now what happens down here on this red loop is that I smoothly traverse the space of all the possible codes, and by that implement a logical Clifford gate. So logical Clifford gate means that I exchange the homology elements of these two logical loops up here in some manner through some deformation, and I do it by always staying at least some constant away from this topological defect within the three-sphere. Yeah, so this is exactly the kind of picture that explains fiber bundle fault tolerance. Yeah, okay, maybe I shouldn't say much more about this. Okay, so that's a general picture. So I haven't talked about some of these things. I haven't talked about so much, but you can think. But what we have is that we know that GKP codes, and I've tried to motivate at the beginning that you can extend this to all stabilizer codes. You can think of in terms of symplectic lattices, or symplectically weakly self-dual lattices, and by compactifying complex space with these lattices, you end up with Riemann surfaces that capture the same information. Logical gates, or in particular logical Clifford gates, are given by symmetries or automorphisms of these lattices, which correspond to automorphisms of the corresponding compactified tori that we've looked at. Now, to understand fault tolerance, we look at the space of all those possible lattices, or all the possible tori, and we find that a sufficient necessary classification for fault tolerance is precisely that you have a topological defect in exactly that space of the tori, so that logical Clifford gates are implemented by non-trivial homotopy elements in the space. Yeah, so here we have a connection between something discrete, lattices, and codes that we work with to fault tolerance through an understanding of symmetries. Yeah, that's why I made this allure to the Rosetta stone. Right? In this, yeah. So I mean, you can draw those pictures a bit further. One thing that I want to emphasize that I think is pretty cool about this picture is that all this fuss about elliptic curves and algebra. I mean, you can build a higher mode version of all of this, and you get richer structures. But all of this fuss and all of this fancy math in physics, you typically find in string theory, right? Like you typically have to look at like very complicated things that are absolutely impossible to test physically, and where experiments also like not a possibility. in order to, like build a bridge between math and physics in this rich field. It turns out that coding theory, as I've exemplified in this talk, exactly provides a kind of a tabletop bridge between physics and this kind of fancy math, specifically on experiments that don't need some supernova or a big CERN, but precisely builds on experiments that we are doing today. Right? And that I think is a cool link. Right. Okay. There's some stuff about physics that I'm going to skip. So it turns out that there's also a link between GKP code and corner Hall systems, which is even richer and more complicated. But I think I've already gone over time, so I'm going to skip this and my talk. And yeah, I thank my collaborator Ansgar, who's a gifted PhD student, also here in Berlin. He also writes about this stuff a bunch, and Steve. Yeah. So yeah, if there are any more questions, I would be happy to answer.
Wow, very nice talk, Jonathan. This was very, I think, yeah, like it seems quite dense in the middle and and all, but yeah, you quite nicely explained and yeah, quite pedagogical. So if people have any, I mean, people ask question along the talk, but let's say if they have any question remaining or something, they could unmute and ask. And if there are no questions, then in that case, let's just thank Jonathan for such a nice talk. And yeah, I mean, I see, Jonathan, you are already in Discord, so maybe you could share your slides. There is a channel called Talks. So maybe you could add it there, and later, we will add your recorded videos in the YouTube, yeah, and share with everyone. Yeah,
sure.
Thanks a lot. Thank you. Yeah.
Yeah, pleasure.
Yeah. Thanks.